we continue our discussion on the theorems that will help us to solve electrical networks with the superposition theorem. To understand the superposition theorem, let us consider this circuit. This circuit consists of two power supplies, one having 6 volts and an internal resistance of 0.5 ohms, the other having 12 volts and an internal resistance of 1 ohm. There are 3 resistors 2.5 ohm, 2 ohm and 6 ohm connected in the circuit, and the current that is flowing through the 2.5 ohm resistor is assumed to be I1. The current that is flowing through the 2 ohm resistor is assumed to be I2. When these two reach node A, that will combine and flow as current I through the 6 ohm resistor. Again, when the current meets the node B, it splits into I1 and I2, which then completes the circuit. Then what superposition theorem states is that this circuit can be considered to be the superposition of two individual circuits with the power sources considered separately. That is, in the first circuit, we have only the 6 volt power supply having 0.5 ohms internal resistor, and the currents that are flowing in the circuit as I1 dash, I2 dash, then I dash. The other circuit has only the 12 volt power supply having internal resistance 1 ohm, and the currents that flow in the circuit are designated as I2 double dash, I1 double dash, then I double dash. That is, according to this theorem, in any linear bilateral network with multiple power sources, the response across any element in the circuit is the sum of the responses obtained from each source, which are considered separately. In other words, we can analyze any electrical circuit by evaluating each power source individually and then combining their effects algebraically. Let us see how that can be done. Figure A shows the circuit that need to be solved using the superposition theorem. In the first step, we'll remove the 12 volt battery from the circuit, retaining its internal resistance of 1 ohm. So that is shown in figure B. In the original circuit, the current that is flowing across 2.5 ohm is I1, current that is flowing in the 2 ohm resistor is I2, and that flowing through the 6 ohm resistor is I. Now, in the modified circuit, which is having only one power supply, that is 6 volts, the current that is going to flow through the 2.5 ohm resistor will be designated as I1 dash, and that flowing through the 2 ohm resistor will be designated as I2 dash, and that flowing through the 6 ohm resistor will be designated as I dash. At node B, I dash and I2 dash will combine to result in current I1 dash that will complete the circuit. And in this circuit, we'll find the various currents by applying the Ohm's law. In the third step, we will replace the 6 volt battery with its internal resistance. That is, we have removed the 6 volt battery from the circuit and have retained the internal resistance of 0.5 ohms. In this case, the current that is flowing through the 2 ohm resistor is assumed to be I2 double dash, that through the 2.5 ohm resistor is I1 double dash, and the current that is flowing through the 6 ohm resistor is I double dash. As in the previous case, we'll find the various currents in the circuit. In the final step, we'll combine the current values obtained from figure B and figure C, and the actual values of the currents in figure A will be the superposition of these currents. That is, I1, which is the current that is flowing through the resistor 2.5 ohm, will be the superposition of I1 prime. I1 prime is the current that is going to flow through the 2.5 ohm resistor when we have only the 6 volt power supply, minus I1 double prime. where I1 double prime is the current that is flowing through the 2.5 ohm resistor when we have only the 12 volt power supply in the circuit. Similarly, we can write I2 as the superposition of I2 double prime minus I2 prime. You may think that why it is not I2 prime minus I2 double prime. That is because the direction of I2 and then I2 double prime are the same. Therefore, we will take I2 as equal to I2 double prime minus I2 prime. And the total current I that is going to flow through the 6 ohm resistor would be the sum of I prime and then I double prime. That is equal to I prime plus I double prime. So this is a method of evaluating various currents in a circuit by using the superposition theorem. The general statement of the superposition theorem therefore goes like this. In a network of linear resistances containing more than one generator or source of EMF, the current which flows at any point is the sum of all the currents which would flow at that point if each generator were considered separately and all the other generators replaced for the time being by resistances equal to their internal resistances. To get a better understanding of the theorem, let's work out this problem. Find the different currents flowing in the branches and voltages across 6 ohm resistor using the superposition theorem. That is, we have to find out the value of I1, I2, then I, and also the potential drop across the 6 ohm resistor. The original figure has been shown on the left. In the first step of solving this circuit by using the superposition theorem, we will remove the 12 volt battery, retaining its internal resistance of 10 ohm. As you see in this figure, the 12 volt supply has been removed, but we have retained the 1 ohm resistor. Now the current that is caused in the circuit by the 6 volt power supply, which is I1 prime, can be found out by applying Ohm's law. For that, we have to combine all the resistors in the circuit. When we inspect this circuit, we can see that the 2.5 ohm resistor is in a series combination of the parallel combination of 2 and then 1 with the 6 ohm resistor. So the 6 ohm resistor is in a parallel combination with the 2 and 1 ohm resistors. We will first find out the equivalent resistance of the parallel combination of the 6 and 3 ohm resistors. That is equal to 3 parallel 6 in short form, and this is nothing but 3 multiplied by 6 divided by 3 plus 6, and this is equal to 18 over 9, and that is equal to 2 ohms. The total resistance includes the internal resistance of the 6 volt power supply, that is 0.5, and then resistor 2.5, which is in a series combination with this 2 ohm resistor that we have just calculated. So the total resistance in the circuit turns out to be 5 ohms. Now the current I1 prime can be found out by taking the ratio 6 divided by 5, and that is equal to 1.2 ampere. That is, when we have only the 6 volt power supply, which is having an internal resistance of 0.5 ohms in the circuit, the total current that is going to flow in the circuit is given by 1.2 ampere. When I1 prime reaches node A, it divides into I2 prime and then I prime. We can find I prime and then I2 prime by using the current divider rule. According to the current divider rule, the current I prime is given by total current, that is total current is I1 dash multiplied by resistance in the other branch. So this is the other branch. So the resistance in the other branch divided by the total resistance in the loop, that is 6 plus 2 plus 1, and we found the total current as 1.2 amperes. That multiplied by 3 divided by 9, which gives us 0.4 amperes. Now the current I2 is given by total current, that is I1 prime, multiplied by resistance in the other branch. So the resistance in the other branch, this is 6 ohms, that is 6 divided by total resistance in the loop. The total resistance in the loop is 6 plus 2 plus 1, which is equal to 1.2 multiplied by 6 divided by 9, and that is equal to 0.8 amps. That is, we have found out the various currents in the circuit, which consists only of the 6 volt power supply. Now we have to perform the same procedure with a circuit consisting only of the 12 volt power supply. In the next step, we will replace the 6 volt battery with its internal resistance. So in the resulting circuit, we have only the 0.5 ohm resistor, and we have retained the 12 volt 1 ohm power supply. The various currents in the circuit are I2 double prime and then I1 double prime, and the current through the 6 ohm resistor is assumed to be I double prime. Now the various directions of the currents in the circuit. For the calculation, we can assume any direction for the current flow, and we'll get the direction of the actual current after solving the circuit. That is, the sign of the current will be positive or negative, and accordingly we can determine the actual direction of the current. We'll now find the total current I2 double prime by applying the Ohm's law. We see that the 2.5 and 5 ohm resistors are in a parallel combination with the 6 ohm resistor, and this parallel combination is in series with the 2 ohm resistor. We'll first find out the equivalent resistance of the parallel arm. In the parallel branch, we have the 2.5 and 0.5 ohm resistors in a parallel combination with the 6 ohm resistor, and this is 3 in parallel with 6 ohm resistor, and then when we calculate the effective resistance, that will be 3 multiplied by 6 by 3 plus 6, and this is equal to 2 ohms. And the total resistance in the circuit is 1, which is the internal resistance of the 12 volt power supply, plus 2 plus 2, and that will be equal to 5 ohms. So we have simplified the circuit to be like this. The total resistance is 5 ohm, and the current that is flowing in the circuit is I2 double prime. This is 12 volt. When we apply the Ohm's law, we will get the current I2 double prime as 12 divided by 5, and that is equal to 2.4 amperes. We now have to find out the currents I double prime and then I1 double prime by the current divider rule. When we use the current divider rule, we will get I double prime as equal to the total current in the circuit, that is I2 double prime, multiplied by resistance in the other branch. So this is the total resistance in the other branch. So that is 0.5 plus 2.5 divided by total resistance in the loop, which is 2.5 plus 0.5 plus 6. That is equal to 2.4 multiplied by 3 divided by 9, which gives us 0.8 amperes. Now the current I1 double prime is given by the total current, that is I2 double prime, multiplied by resistance in the other arm. So this is the other arm, that is 6 ohm divided by total resistance in the loop, that is 2.5 plus 0.5 plus 6, and this is 2.4 multiplied by 6 by 9, which is equal to 1.6 amperes. So we have analyzed the circuit with a single power supply at a time. So in the first circuit we only had the 6 volt supply, and in the second circuit we only had the 12 volt power supply. Now according to the superposition theorem, these two circuits will combine to result in the circuit that is given in the problem. Therefore, I1 is given by I1 prime minus I1 double prime. So this is minus I1 double prime because the currents are in the opposite direction. When we calculate, this will be 1.2 minus 1.6, which is equal to negative of 0.4 ampere. And this is a charging current. That is, the actual direction of I1 is in the opposite direction. And I2 is equal to I2 double dash minus I2 dash. You might think, why this is not written like I2 dash minus I2 double dash. This is because the assumed direction of I2 and I2 double dash are along the same direction. Therefore, in writing I2, we'll take I2 double dash minus I2 dash. And this is equal to 2.4 minus 0.8, and that is equal to 1.6 amperes. And the current through the 6 ohm resistance I is given by I dash plus I double dash, and this is equal to 0.4 plus 0.8, that is equal to 1.2 amperes. The voltage drop across a 6 ohm resistor is given by 6 multiplied by 1.2 amperes, that is equal to 7.2 volt. We'll conclude this session with a discussion on the theory of current divider rule. So we have a circuit in which the total current is I, and at this particular node it has been divided into I1 and I2. I1 flows through resistor R1 and then I2 flows through resistor R2. We want to find out I1 and I2. So at this node, the total current I is equal to IR1 plus IR2. We see that the same voltage appears across R1 and R2 because they are connected to the same points. Therefore, we can write I as equal to V divided by R1 plus V divided by R2. This is V multiplied by 1 by R1 plus 1 by R2, and that is equal to V multiplied by R1 plus R2 divided by R1 multiplied by R2. From where we can find the total voltage as I multiplied by R1 R2 divided by R1 plus R2. Now we will solve for IR1, where IR1 is equal to V divided by R1, and that is equal to I multiplied by R1 R2 divided by R1 plus R2 multiplied by 1 over R1. The R1s get cancelled, resulting in the current IR1 as equal to I multiplied by resistance in the other branch, that is R2, divided by R1 plus R2, which is the current divider rule for the current that is flowing through the resistor R1. We will now solve for IR2, which is IR2 equal to V divided by R2, and that is equal to I multiplied by R1 R2 divided by R1 plus R2 multiplied by 1 over R2. R2's get cancelled, resulting in I R2 as equal to I multiplied by resistance in the other branch, that is R1 divided by R1 plus R. So this is how we frame the current divider rule.